All right, guys, so let's do a real quick recap from yesterday. Yesterday we started looking at the different parts of an atom and isotopes. And one of the big things that you need to be able to do is to be able to determine how many protons, neutrons, and electrons are in an atom of a certain isotope. So looking at number one, want to know how many protons, neutrons, and electrons are in an atom of chlorine-39. Remember, whenever it's written this way, that 39 is our mass number. So if you look, chlorine on the periodic table is number 17. Remember that atomic number means that there are 17 protons. And unless you're told this has a charge, you assume that it also has 17 electrons, because remember, the positive and negative charges have to cancel out. The one that's a little bit harder to find is the neutrons. So remember, this mass number is protons plus neutrons. So if we take the 39, subtract our number of protons, subtract our atomic number, which was 17, we get that this has 22 neutrons. Looking at number 2, this is the same thing, but now we have our isotope written in that AZX form. So remember, that top number is our mass number, bottom number is our atomic number, and then our symbol of our element. So we're looking at how many protons, neutrons, and electrons are in an atom of, it's lead with the mass number of 210. So remember, this bottom number is our atomic number. So that tells us protons. So we have 82 protons. Also 82 electrons, because this does not have a charge. Then looking at our mass number. So remember that 210 is protons plus neutrons. So if we subtract the 82 protons, we get that this has 128 neutrons. So this is very similar to what you were doing in the homework yesterday, and you should be able to do this on your own. All right, so switching over to our notes for today, picking up where we left off yesterday, we talked about finding the number of each type of subatomic particle, and we looked at the mass number, which was the mass of the nucleus, which only included the protons and neutrons. If you remember, on your box on the periodic table, it also has that mass at the bottom, which most of them are not in whole numbers. So we're going to look at how they get those numbers that are on the periodic table. So when looking at atomic mass, it's difficult to determine the actual mass of individual atoms due to their small size and such a small mass. You can't just pick up one atom, put it on a scale, and figure out what the mass of that one atom is. So we compare the mass of an atom to a standard. So our standard that we use is a carbon-12 atom. With atomic masses, we measure these in atomic mass units, or AMUs. This is equal to 1/12 the mass of a carbon-12 atom. So if you think of carbon-12 has 6 protons and 6 neutrons, that atomic mass unit is equivalent to 1 proton or 1 neutron. In isotopes, atomic mass is represented as the mass number, which is a whole number. And remember, mass number is different for different isotopes. So different isotopes can have different masses, but remember, they have the same number of protons if they're isotopes of the same element. So what is on your periodic table, that mass that is not a whole number, is an average atomic mass. And average atomic mass is not found like you would do a normal average in math. You are not simply adding masses together and dividing by how many masses you have. Average atomic mass is a weighted average mass of the atoms in a naturally occurring sample of the element. So a weighted average means that you may not have the same amount of every isotope. So you have to account for the average of the isotope masses according to their abundance in nature. You might have a lot of one isotope and only a small amount of another. Weighted average, you can think of similar to how a grade is calculated, where you have like 20% quizzes and homework, 20% labs, 60% tests, or whatever your percentage is. Because tests are that higher percentage, they count more for your actual grade. Same kind of thing deals with average atomic masses. So to find average atomic mass, you need to know the number of stable isotopes of an element, the mass of each isotope, and the percent abundance of that isotope. So every substance has at least 2 isotopes. Some of them might have up to 5. We typically don't deal with those very often. But to calculate the atomic mass of an element, we're going to take the mass of an isotope, multiply that by its percent abundance. And this does need to be written in decimal form. So you have to move the decimal from the percentage to change it back into a decimal to put it in. And that will be done for each isotope. And then once we've done that for each isotope, we're going to add our products together to get that average atomic mass. All right, so let's look at an example of how this works. And like I said, for each isotope, we're going to have to do mass times percent abundance, written in that decimal form. Oh, excuse me. I can't spell today. There we go. So here it tells us element X has 2 natural isotopes, tells us an isotope with a mass of 10.012 AMUs, which is the isotope of X10, has a relative abundance of 19.91%. The isotope with a mass of 11.009 AMUs, or X11, has a relative abundance of 80.09%. Calculate the atomic mass of this element. So it tells us we have 2 isotopes. We have X10 and X11. So we're going to have to do the mass times percentage twice. We have to do it for each isotope. So for X10, it gives us a specific mass of 10.012. If it did not give us that mass as a decimal, we would just use that mass number, that 10. It tells us that that has a percent abundance of 19.91%. Well, to change it to a decimal, just move it back 2 spaces. So this is going to be 0.1991. So that isotope has a relative mass of 1.993. And I would keep several decimal places as you're going through this. Because if you round too much, it skews your answer too much. Looking at the next one, X11, it tells us has a specific mass of 11.009 and has a percent abundance of 80.09. So if we move the decimal back 2, that is 0.8009. So when we multiply those together, we get that this isotope has a relative mass of 8.817. And these are in AMUs. And we said our last step was to add those products together. So we're adding the products for each isotope together. And we get that that has an average atomic mass of 10.810 atomic mass units. And we could match this up and figure out what element this is. So if you look at the masses on the periodic table, this would actually be boron, which is number 5 on the periodic table. So we could use this to identify what that unknown element is as kind of a secondary question. All right, let's look at this problem. Here it tells us the element copper has naturally occurring isotopes with mass numbers of 63 and 65. The relative abundance in atomic masses are 69.2 or 69.2% for the mass that is 62.93 AMUs and 30.8% for the mass that is 64.93 AMUs. Calculate the average atomic mass of copper. So same deal, we have 2 isotopes. We have copper 63 and copper 65. So for each one, we are going to do that mass times percent abundance. So copper 63 has an actual mass of 62.93. Its percent abundance is 69.2, so move the decimal back 2 spaces. That's 0.692. So when we multiply those together, we get that that isotope has a relative mass of 43.548. I'm going to keep several decimal places. Looking at the next one, the copper 65, it has a mass of 64.93. Multiply that by the percent abundance of 30.8, so 0.308. And when we multiply those together, we get that this isotope has a relative mass of 19.998. Our last step is to add them together. And I got that our average atomic mass is 63.546. And that is AMUs, or atomic mass units. A way that you can check yourself is it told us this is copper. Copper on the periodic table has a mass of 63.55. So our answer should be close to that. But you have to show the work because it may not be exactly what is on the periodic table. But that's a way that you can check to see, you know, if you're very far off, maybe you forgot to move the decimal 2 spaces. Maybe you only moved it 1. That's a common mistake, especially whenever we have a single digit percentage. People forget to move it 2 spaces whenever they're changing into a decimal. All right, let's look at this last one together. Says calculate the atomic mass of bromine. The 2 isotopes of bromine have atomic masses in relative abundance of 78.92 AMUs, has a percent abundance of 50.69%, and 80.82 AMUs has a percent abundance of 49.31%. So our 2 isotopes are bromine 79 and bromine 81. So the bromine 79 has a mass of 78.92 times a percent abundance of the 50.69 is going to become 0.5069. So that has a relative mass of 40.005. For the bromine 81, that has a mass of 80.92. Our percent abundance is the 49.31. Move the decimal, that becomes 0.4931. And that has a relative mass of 39.902, When we add those together, we get a relative mass of 79, or an average atomic mass of 79.907 atomic mass units. And yet again, you can check bromine on the periodic table is 79.90. So we're pretty close. One thing that you'll notice is whichever isotope has the higher percentage, that tends to be what the average atomic mass is closest to. This one is split pretty evenly. Whereas in our last one, that higher percentage was the copper 65, or excuse me, copper 63, and copper's average mass is closest to 63. So whichever one has the higher percentage tends to be what the average mass is closest to.